Welcome to the Dynamometer Testing eCourse. My name is Sean Dawsey. I am the creator of this course, and I will be the instructor just floating around down here on the bottom of the slide as I guide you through the material. So if you want to tell anybody about this course, if you want to say, hey, there's this really great online course you can take, you can tell them to go to dynocards.com, and that will link over to this course hosting website. So let's go ahead and jump in. Now, in this course, I'm going to open up to you the full library of knowledge when it comes to dynamometer cards. Of course, we're going to get good at interpreting the shapes of the dynamometer cards, but we're going to look at much more than that. We're going to look at the elasticity of the rod string. Of course, we have to understand the downhole pump to understand dynamometer cards. We're going to look at rod loading and valve test and all sorts of things, everything that's related to dynamometer testing. We're going to look at that in this course. And if you want to know what topics are going to come up in what order, you can look at the detailed course outline. And when you open that up, you might think, wow, this is a lot of information. And it is. But as the great Thomas Paine once said, the harder the conflict, the more glorious the triumph. And I promise you, at the end of this course, you will have a glorious triumph if you listen, take notes, and think about things as we go through it. Don't just watch me or listen to me explain it. Actually pause and think through it yourself and test your own knowledge. And of course, make sure you take the quizzes that are at the end of this course to ensure that you've practiced that knowledge and you're actually testing it yourself. But you'll become an expert when it comes to dynamometer related testing. So let me tell you just a little bit about myself. So I graduated from Texas A&M University, which is just outside of Houston, Texas. And I graduated with a petroleum engineering degree in 2009. And then I moved out west to Midland, Texas. And I've been out in Midland, Texas since I came out after graduation. But I started off working for a smaller company, Discovery Operating. You've probably never heard of them unless you live out here in the Midland area. But it's a decent sized company. I mean, they operated about 250, maybe 300 wells when I was working there. They've been around for about 45, maybe 50 years even now. And it was a great fit for me. When I started out, I was basically thrown out in the field. I got lots of field experience, which is the best thing you can do for a graduate engineer, is like go see the actual oil field. But I was generally a production/operations engineer for the first 3 years. And then they made me the production manager for the last 2 years after they saw my interest in trying to optimize our artificial lift system. So when I was a young engineer, fresh out of university, I've never been the smartest, but I've always worked the hardest, and I wanted to apply myself. I wanted to grow in my career, and I started studying rod pumping systems primarily because that was the main form of artificial lift that we employed at the oil company. And so I started studying everything I could, and eventually I got to a point where I knew all the theory. And there was one Saturday in particular where I was sitting in the downtown library. They had a great petroleum section, and I was reading the same material that I've read before. Of course, it was different papers or different books, but I already knew all the theory on it. And I was thinking, why am I here in the library on the weekend when I could be out at the wells and actually I could make the field my laboratory? And so at that point, I decided, I know the theory. I need to go out and get more hands-on experience with the wells. And I talked my operator into buying an echometer, fluid level gun, and dynamometer system, and started running around, testing the wells, playing around with them. And based on the feedback that we were able to get back from those sort of tests to see what was going on downhole, I ended up implementing a lot of changes, especially when it came to downhole gas separation, which was a major problem that we were experiencing. And to some degree, we knew there was some of that, but not to the full extent, but made a lot of changes with respect to that, and also trying to optimize the run life on our wells, and had some great success. So anyways, that's kind of my backdrop in my field experience at Discovery Operating. So I left Discovery Operating in 2014. I also became a professional petroleum engineer in 2014, which means that I took a very hard competency exam to prove that I'm competent in my knowledge on petroleum related topics. I can serve as an expert witness in litigation type matters as a result of that. I got a cool stamp too that I can put on some of my work. More importantly though, in 2014, I started my company, Downhole Diagnostic. So if you've ever seen my company logo or my company name, that means anything you see from that came from me. If it's my rod pumping brochure or all the information on my website, I put all that stuff together. Now, what I pretty much do at Downhole Diagnostic is I promoted myself from being an office engineer for the most part, to being a field hand. I'm going out to the wells for many different customers that I have out here. I'm taking fluid level shots. I'm doing dynamometer tests. I'm looking at their POCs. I'm verifying the POCs are drawing accurate cards. I'm trying to assist in the optimization of the settings for the POCs. In general, I'm trying to help my customers understand where their wells are at and what is the best way to optimize them to extend the run life on those wells, but also to maximize the production. We want to maximize the profitability on those wells. But primarily, it's out doing field testing like this. I also do some consulting work when it comes to artificial lift design, primarily related to rod pumping systems. And then I also do some artificial lift related training, as you can see right here with this course. So if you look at my company name, I picked it for a very particular reason. Downhole Diagnostic. I like that in the fact that it's descriptive. It tells you what I do. I try to diagnose the downhole. But if you look at the etymology, I also really liked that. Dia means through, and Gnostic means wisdom. And there's a connotation with Gnostic, if you look at the kind of the religious sect of the Gnostics back in the 1st century, which are quite interesting. But the connotation to Gnostic means kind of esoteric or hidden wisdom. And that's what I try to do with my customers. I try to, through the esoteric or hidden wisdom that I have, the complete understanding of rod pumping systems, I try to go downhole and extract out the most value, and then create a kind of a historical understanding and a narrative of how the well is operating and where the well needs to be optimally to maximize its profitability. But anyways, this is kind of a quick rundown on my work experience. So before we get into the rest of this introduction, let me just please say that this is copyright protected. Please do not copy, share, or reproduce this course in any form or fashion. I would greatly appreciate it. So the videos that you're going to be watching in this course, excluding this first introductory video, which is a newly re-recorded video, but the other videos are extracted out or lifted out of my 50 to 60 hour masterclass on rod pumping diagnosis and optimization. And in that class, I talk about fluid level shots. I do the dynamometer test, the stuff that you're going to see here, but I also go into gas and solid separation, POCs and automation, extending run life or just general troubleshooting and optimizing wells. But it's a much larger class. But the reason I'm telling you that is that I spent over 5 years putting that together. And I've invested a ton of time in putting this material together. So please do not violate the copyright and please support my work. Throw some money at me to try and make up for how much time I put into this course. You wouldn't even understand how much of my life it's consumed over these last 5 years. Now, this course is designed to be computer-based. So the size of the font, the size of the images are designed for you to be sitting at a computer. If you want, you can try to watch it on your phone. It's not going to probably work out too well. But what might not be a bad idea is if you were to watch a class, and then if you wanted to review it, maybe you could stream it while you're bumping down a lease road driving out to a well. But it's designed for you to be sitting at a computer. Also, it's not designed to where you buy one access link and then you share it around with 10, 15 other people at your company and throw it on a projector screen. I would appreciate, as I mentioned, please support my work. If you have multiple people that want to sign up for the class, I can give you a bulk rate discount for multiple students. So here is the section outline for this course. We are in the introduction right now, and the next sections are as listed below. And so I'll quickly read over these, and then in the next slides, I'll show you pictorially what the main topics are that we're going to discuss. So the second one is downhole pumps and rod pump operation, is 2 hours. Then we've got dyno part 1. Primarily, this is card interpretation. Then dyno part 2, we're going to be going overtime into some various topics. Then the final quiz. And then after that, notice after the final quiz, we have another section, echometer equipment and software if needed. This is 3 hours. And so I included this just in case you want to take it. You certainly don't have to. This is focused mainly on comparing the wired equipment versus wireless equipment. And really the most substantial part of this section here, I think about 2 hours, is reviewing the different software packages that Ecometer has. So it's the old software, TWM, and the new software that they have. So if you're interested in those, you want to better understand the software or how to navigate through it, you can watch this. And if you do want to take this, you might slide this in right up here on top and take that first, but you don't necessarily have to. So anyways, that's for your benefit if you want it. But let's go ahead and jump into the second section to see what we'll discuss. This is downhole pumps and rod pump operation, and this is going to be a primer before we can start getting into dynamometer cards. We need to understand the downhole pump and the whole rod pumping system, and the fact the rod string is picking up and dropping down the plunger that's reciprocating up and down of this barrel. We need to understand this process first. So what we'll look at first is the pump components and valve action. So if you look at a schematic of a pump, okay, we've got our plunger right here with our traveling valve. The standing valve is in the bottom of the barrel, and we have 3 different pressures across the pump. We've got the pressure of the fluids that's coming into the pump. This is our pump intake pressure. On top of the pump, or on top of the plunger, we have the pump discharge pressure. That'd be the pressure at the bottom of the tubing. And here, this is the pressure inside the pump chamber. As the plunger moves up and down, it creates differing pressures, which are going to cause these valves to open and close. And we're going to learn exactly why those valves are opening and closing. So we'll look at the valve action. So if a ball is sitting down on the seat, that means it's closed and potentially it's holding the fluid load. And if the pressure below a valve is greater than the pressure above, what happens is with the balls and seats here, they're one-way check valves, they're going to open up though. So if the pressure down here is greater, fluid is going to flow through that valve and it's going to push the ball off the seat. So we're going to focus on the pressures that are actually occurring as the pump reciprocates, or the plunger reciprocates up and down. We'll look at the pump capacity. How do you calculate the production? Pretty straightforward. We'll also look at slippage in the Patterson slippage equation. So if you, on the upstroke, as the plunger is moving up, the pressure differential starts to form across the plunger assembly. That's going to cause fluid to slip down here between the plunger barrel clearance. And on the, we call this slippage, and by the top of the stroke, you can see that some of the fluid has slipped down beneath the plunger, and this is going to be the slippage that's occurring. So we can measure what the actual slippage rate is, and there's an accurate equation that was based on a lot of testing that we'll discuss as to what variables go into causing the slippage to occur between the plunger and the barrel clearance. Then we're going to look at the fluid load, which is abbreviated F sub O, and that's equal to the pressure differential across the plunger times the area of that plunger. But we'll look at how the fluid load can cause rod stretch and affect the downhole stroke length. And we'll look at other factors, including the over travel that affects the downhole stroke length. So here we have 2 different sets of dynamometer cards. And you can see this one, this is a very wild set of dynamometer cards. This is a over travel card where it's 192-inch stroke length at surface, but the downhole stroke length is showing up to be 285 inches, which is really just unbelievable. I've never seen anything like this. This has all fiberglass sinker bar rod design, long stroke length, and it's running fast. It's running about 10 strokes per minute. Also, it's got a very low fluid load because it has gas interference. But you can see that the downhole stroke length is radically different than the surface stroke length. Same thing for this one. The downhole stroke length is radically different from the surface stroke length, but in the opposite direction. You can see how much shorter it is downhole. We're only getting 50 inches of travel. This is due to a bad design. We've got too much rod stretch occurring in that system to where we're not effectively getting the displacement or movement of that plunger from the surface stroke length down to the downhole plunger stroke length. So we'll look at stretch and over travel, and we'll look at how to calculate the downhole stroke length in this section. And we're going to focus a lot on the fluid load transfer in this section. So every stroke, the fluid load transfers back and forth from the tubing to the rods and back. And you can see the rod stretch that shows up on the surface card. The surface card will tend to line up as long as there's not too much dynamics and a few other things that we'll talk about. It'll tend to line up with the rod spring constant, which represents the stretch that's occurring in that rod string. And also you can see tubing movement or tubing stretch. That's going to show up in your downhole pump card. This is what we call our tubing spring constant right here. So these are the topics we will talk about in section 2, and this is going to give us a good primer for how the pump works, how the system operates, and help us in section 3, where we start off with dynamometers, looking at card interpretation. So there is the surface card. This is the load versus position on your pumping unit, and you can have wildly different surface cards. We'll focus on surface cards and understand what is going in to the shape of a surface card. Now you can see these two surface cards are radically different right here. But if you were to calculate what's actually happening down at the very bottom of the rod string, if you were to look down through it with the wave equation for both of these wells right here, the downhole pump card looks essentially the same. It's an ideal card, a nice rectangle right here for both particular wells. So the surface cards can be quite variable, but the downhole pump cards are quite standardized in shape. And this is why people like to interpret what's happening in their well by using the downhole card, because you're taking out a lot of the variables that cause the changes to the shapes that you can see here in the surface card. And we will focus on two specific things when it comes to surface cards, because there's a lot of value in the surface card. Most people neglect them and don't even look at them. But we'll look at stuffing box friction and identifying light tags. Here's an example of stuffing box friction in the surface card. You can see it with the vertical transition at the end of the stroke, and that's creating these crazy kicks at the end of the cards. It's also causing the card, the pump card, to be taller than it should be. And so it's showing a higher fluid load in the card, even though it's not really fluid load. It's just excess friction showing up in the downhole card. And these have some wild kicks right here because of the rod string it's calculating down through. This one has fiberglass, but we'll talk about that in this section. Also, we'll look at identifying light tags with the surface card. Here is a pump card. It has a very light tag, and you can see it. It's also evident in the surface card, but on a lot of wells, it's not always as evident in the pump card because you have various different things that can obscure it. If we look at this particular well right here, though, on the previous strokes where it wasn't tagging, so that would be here, the black lines, you can see it's nice and smoothed out, but when it does have that tag, you can see that sharp drop right there. That's the stroke where it tagged. The other strokes, it didn't. But I'll show you different examples, and we'll talk about why sometimes you can see tags in the surface card, but it's not obvious in the downhole card. Then we're going to go into pump card shapes, and this is probably what you're most interested in. Because based on all these shapes, you can see exactly what's going on downhole. We have a delayed traveling valve closure. We got solids grinding between the plunger and the barrel. A pump that's gas locked. Fluid pound. We don't have enough liquid to fill the pump chamber. We have a lot of slippage, indicating the pump's probably worn. And this one right here indicates incomplete liquid fillage. You can see this is the compression in the pump chamber. And so that's either fluid pound or gas interference. But what stands out about this is this big fat panhandle. That indicates there's a lot of excessive friction in the system, probably happening on the rod string higher up in the well, but it wasn't stripped out, and so it's plotting in the downhole card. But based on the card shape, you can interpret all sorts of things as to what's happening downhole, both what condition your pump is in and what conditions it's operating in. So we'll learn every card shape that's out there. After that, we're going to look at combination cards. So you can have multiple things occurring at the same well. If you combine a fluid pound card with a slippage card like this, you can get a card that has a can opener shape like this. So we'll look at various different combinations, and I'll show you some real world examples where you have to disentangle multiple things that are occurring in that system at the same time. That'll also be a good review to make sure you understand all the basic card shapes when you only have one factor occurring at the same time. And then at the end of this section, we're going to look at different types of load cells or dynamometer systems. So probably the most common one out there is going to be your POC system, because this is on all sorts of wells and it's recording dynamometer cards for every stroke. You can also have temporary install dynamometers like these two from eCourse. This is a compression load cell right here. We call this the horseshoe load cell. And this is the polish rod transducer. If you're using the eCourse equipment, you're probably 99% chance this is what you're using right here. And this device is not as accurate as this one, but in general, for the most part, it's extremely accurate. But there's certain situations where it's not as accurate, and it has limitations, and you have to understand those limitations. Now, when I use dynamometers, I use this one 99% of the time myself because it's so incredibly easy to install and uninstall. But you have to understand the differences between these types of dynamometers and the limitations of this one. Also, the complications of this. Actually stacking out the rod string and installing this is not easy. So we'll talk about different types of load cells and what can create differences in the shapes of the dynamometer card depending on which one you're using. We'll also look at some POC cards in this section. Now, moving on to section 4. This is dynamometers part 2, where we're going to be working overtime. Okay, so the first topic here is we're going to talk about stress versus strain. And what does that mean? Well, that means when you apply a load to a rod, it has a stress. So that's the load divided by area. And it's going to have a strain. It stretches. When you apply a load, it stretches. Okay, well, this is kind of the basis, the introductory framework to get into rod loading. So if you look at a rod string, let's just say we got maybe 7/8, 3/4, and 1.5" sinker bars here on bottom. As this rod string reciprocates up and down, it's going to experience a minimum load. Each rod on these tapers is going to have a minimum load experienced, and then also a maximum load experienced. And that minimum load is probably going to occur somewhere around the middle of the downstroke, maybe a little bit before it, when it's got a faster acceleration rate. But you can look at what the minimum load is versus depth going down. And of course, the load on the rod string drops with respect to depth because this rod has to carry all the rods beneath it. Your bottom sinker bar here doesn't have any rods beneath it. It's just connected to your plunger on bottom. But let's say that this is the minimum load experience going down that rod string on the downstroke. Now on the upstroke, you're going to have a higher load because friction's opposing the motion. Also, the fluid load is being picked up on the upstroke. So if we were to plot what the peak load is for all of these rods going down the rod string, you can see that you have a higher load, but it's the difference between the two, which is going to be twice the friction in the system plus the fluid load. But there is a alteration or a cyclic load that is occurring each stroke. On the downstroke, you have a minimum load, and then on the upstroke, you have a peak load, and the loads are cycling back and forth. And this leads to fatigue failures. Now we have a design guide that tries to help guide us as to what is the appropriate load for a particular type of rod, and that's called the modified Goodman diagram. And this is what it looks like. You probably have not ever seen this unless you've studied it, because for the most part, you just plug it into a computer program and you run a simulation and it tells you what your rod loading is. Well, it's based on this triangle. We're going to look at how rod loading is calculated. But if I take these loads right here, for example, if I take the minimum load experienced by this top rod, and if I divide by the cross-sectional area of it, I will get a stress. And I can come down here in this ratio with that stress right there, and I can put a dot as to where that lines up. And then I can look and see what is the peak load experienced by that rod, convert it to a stress, and with this ratio, I can put a dot here and then connect the two. And based on how high up you go up vertically in this recommended load triangle right here, this is about 80% of the way up to this red line. And so based on that, the rod, this particular rod, the top rod is loaded about 80% according to the modified Goodman diagram. If this top dot went to the red line, it would be 100% loaded. And if it came above, it would be greater than 100% loaded. We're going to talk about the modified Goodman diagram. What's also important is this triangle right here. The modified Goodman diagram is changing currently as I speak. I'm here in the end of 2024. API is modifying it. What's also important is that there's rod manufacturer companies that are playing around with this triangle because it makes their rod look better relative to the competitors. And we'll talk about that also in this section. And we're going to look at fatigue failures. So this is going to be a real interesting one. We'll also look at how fiberglass rods and steel rods are manufactured, but we'll talk about this load variation that occurs that ends up leading to a fatigue of the material that's going to eventually cause a rod part. And usually those rod parts occur at some sort of stress concentration like this, where you have this sort of pit. But this is a parted rod right here. This is where the initiation occurred. We'll look at some of the identification markers as to how to interpret a failed rod and what leads to rod failures when it comes to fatigue failures. After that, we're going to talk about valve tests. So valve tests are a test you can do with the dynamometer where you're stopping the unit on the upstroke. We call that the traveling valve test, and we see how fast the fluid load leaks off with respect to time. That then feeds into a calculation, an equation that will tell you what the overall slippage rate is. You can also do a standing valve test where you want to see no load increase, and that's a way to check and verify that your standing valve is not leaking. It's in good condition, which it shouldn't. Now, it's important to do valve tests because sometimes you have cards that are not necessarily obvious. This right here is a standing valve leak. And there's actually another factor that's distorting the cards. You can see this drop here and this pickup right here. That is due to stuffing box friction distorting the downhole card. But you can see a little bit, the characteristic standing valve leak card, it looks like a bowl. That's the one that you'll typically see in the literature. Most of the time I've seen it, it hasn't looked that way though. You can see that there's a little rounding here, maybe a little rounding here, but not too obvious. But this was verified to be a standing valve leak based on the standing valve test. Or other times you might have dynamometer cards where you look at it and say, wow, your pump's really worn. In this case, it's showing a lot of slippage, but the pump is actually not too heavily worn. The card is shaped this way because the unit is running so slow. Slow strokes per minute, short stroke length, and it's set deep, which means you have a higher pressure differential. This pump actually shows to be in pretty good condition. It was just a little bit worn. Based on the shape of the card, though, you would think, oh my gosh, this thing's heavily worn. We need to change the pump. I'll tell you some stories about where I've made that mistake, and they've had a card like this. They pull the well, you go back and test it, and it looks the exact same because it wasn't the fact that the pump was worn, it's these other factors. So we'll focus on that in relation to the valve test. Then we're going to look at viscous and drag friction. We'll look at this more. We are already will have looked at it to some degree in the first dynamometer section. But the viscous friction is the friction on the surface of the rod string. So here is a heavy oil well. And what's interesting about these cards is notice the surface card almost looks the exact same as the downhole card. And what that indicates is that you have a shallow well and you also have very little dynamics in your system. So I think this was a 1,500-foot well. I believe it was in Colombia. And it was a pumping unit that's running slow enough. I can read, maybe that's 100, so that's maybe 140-inch stroke length. And it was probably running, I don't know, maybe 2 strokes a minute, something like that. But you can see there's very little dynamics, and also there's not much difference between the cards because it's a very shallow well, so there's not much difference in the loading that's occurring downhole at the pump versus what's happening at surface. But this is the default dampening factor. We got a big fat panhandle, but if I increase the dampening factor, okay, the surface card didn't change. Surface card stays the same. Pump card changes. We're taking friction out of the system using the dampening factor. Now, if you have deviated wells, you might see cards like this. The one-dimensional wave equation is not properly accounting for the rod-on tubing friction that's occurring somewhere higher up in that well. This is what we call a shallow friction card. It's evident in the slants of the card. And we're seeing more and more of these when we have a lot of these pad drilled wells, you know, especially in my part of the world, depends on where you're at. But with the horizontal wells where you might have 4 wells on the same pad and you have intentional deviations in the design of the trajectory of the wellbore, but also unintentional ones. And you have lots of rod-on tubing friction and there's just a distortion to the downhole card. So we'll talk about both viscous and drag friction in the system and how that affects the cards. Then we'll look at load reference lines. So eCourse has all these great load reference lines that you can use for quality control and also troubleshooting. Other software programs have some of these, but not all. But we'll look at load reference lines for the surface card, also for the downhole card. And for example, we can use them if you have a well that has a failure. If your well is pumping good, and this is what the cards look like, and then the next stroke it goes to a failure, and then you get a flatline card, and that flatline card is lining up at different places with respect to where it was, or it should be lining up. So here's 0 load on the plunger. This would represent negative load right here. That's a rod part. But based on where these line up here on the pump card, you can also do the same with the surface card. You can interpret what the cause of that failure is. Then we'll look at dynamometer calculations. We'll look at the gas-free fillage line first off. This is in the eCourse software. Some other software programs have something similar, but this is a gas interference card. This is where the traveling valve opens. We usually call that the fillage line. But that doesn't mean everything beneath here is liquid. So eCourse programmed something in to try and approximate. You're compressing all that gas. The traveling valve opened, but this might be your gas-free fillage line. That represents this is all liquid. This is actually compressed gas right here. And the reason that's important is if you want to estimate the production rate off a dynamometer card, well, you need to know how much liquid is in that pump chamber. And so if this is the representative card, this is the average fillage card for this particular well throughout the day, you would need to know where this gas-free fillage line is to properly approximate the production rate. So we'll look at the gas-free fillage line that ties into the estimated production rate, which there's a couple other factors. And then we'll look at the pump intake pressure from a dynamometer test. The usual way that we try to get a pump intake pressure on a rod pumping well is a fluid level shot. The fluid level shot goes, you take a shot down the annulus, it reflects off the fluid level, but you can see below the fluid level as to what the pressure is going to be of the fluid that's going into the pump intake. But we can also use a dynamometer that looks down the rod string and it peers down through the bottom of the plunger to try and estimate what is the pressure of the fluid that is in that pump chamber. So this is very important right here to understand this concept. And of course, all pump off controllers, for the most part, have this capability. Well, they'll show you the pump intake pressure. So to some degree, if it's programmed accurately, you can use it to replace fluid level shots. Then at the end of that, we have a dynamometer quiz to finish off section 4 that is 2 hours long. Now, what's interesting about that dyno quiz at the end of section 4, so going back to our outline, is right after that we have the final quiz, which is 3 hours. And you're thinking, well, why in the world do we have 2-hour quiz here, 3-hour quiz here? Well, remember, these videos were lifted out of my larger class, and I had a lot of different sections in between here. I had kind of a quiz here at the end of the dynamometer section because there's a lot of material related to dynamometer testing. But then here in the middle, I had gas and solid separation. I had an automation section. I had a troubleshooting and optimization section. And then the final quiz came. So anyways, you've got 5 hours of quizzes. Take whatever you want. If you only want to take one of the quizzes, I'd probably recommend this one right here. This one's going to be a little bit more comprehensive and straightforward in the questions, trying to make sure that all the important topics, I have a question on it. There'll be lots of review on dynamometer card shapes. The quiz at the end of this section is a little bit more interesting. I'm kind of extrapolating from some of the topics that we talked about and showing some interesting examples. And I guess that probably happens to some degree in both. I would recommend both quizzes, but the course is for you. Take whatever you want. But this is the outline. And then as I mentioned, here is the echometer equipment and software section, if you want that. So there is a detailed outline that comes with this course, and it's right below this video. If you will scroll down right now as you're watching me, you will find the handouts for this course right below this video. Save those into a folder, especially the course outline. This will tell you every topic that we're going to talk about. So if you want to skip ahead to a certain topic, you are welcome to do that. And it shows everything here along with the video number. So you can kind of see when a specific topic starts. Modified Goodman diagram looks like it's going to start right here at video 4.2. Now, as you're going through this course, realize this, that as I've mentioned again, these videos are lifted out of my other class. The section numbers at the start of each section are just the wrong number. Don't be confused by that. Here are the actual right section numbers, but the, let's see, dynamometers part 2 overtime. Well, what I show is that section 4, it shows up as section 8 on the first slide of the section. Just don't worry about that and don't be confused. Okay, some other information with respect to this course, or at least some references right here. So you'll see lots of papers that are referenced throughout the course. Most of the time, you're going to see this abbreviation at the end. This is the Southwestern Petroleum Short Course. This is an oil industry event that's held in Lubbock, Texas, which is just north of Midland, a couple hours. But it's held every year, usually in April, and it's a fantastic conference. It is my favorite. There's usually about 8 different rooms where people in the industry are presenting different papers on various different topics, and you can pick whichever topics or papers you're interested in and go into those presentations. So you're not all forced into the same room to have to listen to the same topics, even if you're not interested in them. But the other good thing about the Southwestern Petroleum Short Course is they have a catalog of papers, all the papers that have ever been presented going back to 1954, and you can purchase that. I think it's for about $300, and you can get them all in digital form, and they'll come broken down by year. And then you can do keyword searches on them. And that's why I use this so frequently as a reference, because if I'm looking for a specific topic on, say co-rod or asphaltenes or something, I can do a keyword search on it and find lots of papers that reference it. So if you're interested, reach out to them and purchase that yourself. Now, a lot of the papers I do present are echometer papers, and they don't necessarily say echometer. It's got the various people that work at echometer listed there. And it usually has the Southwestern Petroleum Short Course in the abbreviation and the reference, and that's just because that's how I find it. But all the echometer papers are for free, and you can find it here on their website, and they have the best papers when it comes to rod pumping systems, whether that's fluid level shots, dynamometer test, diagnosing, troubleshooting, what's the fluid distribution in a well. They have the absolute best papers, and you can learn a ton just by reading their material. Now, also included is my sucker rod pumping short course. You can see we got a lot of short courses going on right here. But the sucker rod pumping short course, this is what it looks like. You've probably seen it before. It's made its rounds all the way around the world. I hear people reaching out to me all the time about it. But it's 6 pages, and it is the best desk reference when it comes to rod pumping systems. Sometimes in this course, you will see this pop up with my little Dyno King in the abbreviation sucker rod pumping short course page 2. That means whatever I'm talking about, you can find that on the second page in the brochure, so you can highlight it as opposed to writing it down in your notes. And please do take notes in this class. Now, my favorite book in the industry is written by Balmer and Podio. This is the Beam Lift Handbook. What's so good about this book is that it covers every topic related to rod pumping systems, but it has wonderful diagrams and tables and illustrations, and much better than most other books. It gives you lots of great visuals, and it's very attractive in the way that it's presented. But absolutely the best book, I think, related to rod pumping systems. And then my second favorite book, and this is specific to fluid level shots. This is by Dr. Podio, again, same author here, and he's a longtime consultant for Ecometer, a former professor at the University of Texas, and a really great guy. He's been reviewing my online courses, so thank you, Dr. Podio. This was written with Jim McCoy, who is the founder of Ecometer. So this book is great. Now, we're talking about dynamometer systems in this class, but if you want to understand rod pumping wells, you also need to be taking fluid level shots. I have courses on it, but you can also get this book. It's fantastic, and I do recommend it. Now, you will see lots of abbreviations in my rod pumping brochure and potentially also in this course. So, for example, you might see a sentence like this. Now, do not be afraid. So for my rod pumping brochure, you can find the list of abbreviations in the back. And in this course, I will try to always spell it out for you. It should be straightforward. And after you see abbreviation once or twice, you should be able to remember it. But the traveling valve is attached to the plunger, and on the downstroke, the pump intake pressure is compressed to the pump discharge pressure. So I will try to always spell it out for you so that you're not confused while you're looking at these slides. Now, there are some example files that come with this class that you can play around with. We don't work through them together as too much in the dynamometer course as much as I do in the fluid level shot course. But this is an example. So if one of these pops up on a slide, it's a TAM example file. This is the software from Ecometer. It stands for Total Asset Management. You can download it for free from the Ecometer website. Also, the software comes with its own examples, and it's a great way to cycle through strokes while you're looking at wells that are doing different things, whether they're going from 100% fillage to fluid pound, or gas interference, or tagging occasionally. But I have some example files that are included, and when you import them, those example files are in the handouts right here below this video. But when you import them, if you do not change anything or change the name, this is where they're going to import to eCourse examples. Now, some of the examples might not work if you have an old version of the software. So some of the data was recorded in version 1.8.56 of the TAM software. And so if you try to open something and it's not necessarily working, you might want to update your software. And currently, as at the time of this recording, at the end of 2024, TAM 1.9 is out. So if you have 1.9 or anything later, all of these files right here should work. If you want to know what version of the software you have, open up the software, click Utilities. A box pops out, click About right here. It'll tell you what version of the software you have, and you can go to Ecometer's website to update it if you need to. Now, to finish off the introduction, let's quickly do a very quick overview of dynamometer testing. And then also I'm going to give you a very quick crash course, probably one slide, introduction to fluid level shots, because I'm going to talk about fluid level shots quite a bit in this course. Now, why would you want to perform a dynamometer test? Okay, think about it. We have this tool, but what is the value of the tool? Right? What's the selling point? Why would we want to go hook this up to our rod string and go weigh the rod string, as they used to describe it? Well, the main reason to perform a dynamometer test is to determine what condition the pump is in and what conditions it's operating in. Okay, what condition is it in? Well, if you don't know anything about dynamometer cards, remember this now. The rectangle is the ideal card. That's what you want to see. That indicates the fluid load is rapidly picked up. The fluid load is held for the complete upstroke. The fluid load is then rapidly released indicating we have pure liquid in the pump chamber, and then the plunger moves back to the bottom of the stroke. This is what you want to see. So that would indicate, in general, you can verify it with a valve test, but the pump is in good condition. Now this card right here indicates by the rounding that there's a long delay in the pickup of the fluid load, and the fluid load is not held to the end of the upstroke. So it's only this portion of the stroke that is potentially the effective portion. This pump, in all likelihood, is heavily worn right here. So getting back to the statement here, to determine what condition the pump is it in good condition or bad condition it's worn, and what conditions is it operating in? Well, you can have many different cards that indicate, for example, this indicates a lack of liquid filling the pump chamber. The well's pumped off, or you have enough fluid to fill the pump chamber, but you have free gas getting into it, gas interference. Now, another reason to perform a dynamometer test is for optimization. And one of the most critical things to do is to check for gas interference. Now, it might depend on what part of the world you're operating in, but gas interference is a huge issue because it dramatically reduces the efficiency of your system. It's also going to reduce the production rate from your system. But if you have gas interference, you need to know that you have gas interference, so the next time you pull the well, you can try to change something downhole. So for example, maybe you have a well, and this is the dynamometer cards you get on it. Lots of gas interference, and you're holding, let's just say, 1,500 feet of gas-free liquid above the pump. And then the next day, the well has a tubing leak. Well, that's not good. We have to pull it. But at least now we have a piece of information that tells us we have gas interference, and there's something bad with our downhole gas separator design. So you need to know that before you pull the well. So now we can make some changes. Maybe we want to modify something. We need to modify something in our downhole gas separation design to try and minimize the inefficiency related to gas interference. So that's one of the most important, is to recognize that so you can make changes to try and accommodate that. Another very important optimization use of a dynamometer, and this is specifically with respect to a temporary install dynamometer, like like this horseshoe load cell here from eCourse, but is to calibrate the POC cards. So just because a well has a POC on it, and here's an example right here. So here's the POC load cell. You can see the cable that's going back to the computer on the back that's monitoring every stroke. Just because there's a POC installed doesn't mean it's drawing accurate cards. And I see this all the time. Either the data in the pump off controller is not accurate, and you can see that because when you install another dynamometer on there, the cards are looking very different. You know, they laid down the fiberglass rods and they picked up all steel, but nobody updated it in the POC. But quite commonly, or maybe more commonly, it's the load versus position data that can be out of alignment, and that can lead to something known as card rotation. Here's an example of card rotation. This is how the POC card was drawing, and you can see this slant on it right here is very unusual in nature. That's not how it's supposed to look. After calibrating or correcting the load versus position data, fixing the card rotation. We'll talk about this in the course. I talk about this much more, though, in my POC and automation course. But after correcting the card, this is what it looks like. So let's go back to the original card. So with it being slanted like this, okay, it's going to take a long time. It might, let's say the actual pump fillage might go down to 85 or 90% before this slanted line right here starts to correct vertically. So if you want to accurately control the well, you know, don't get below 90% fillage, whatever you set your controller at, you're not going to be able to accurately do it if you're not drawing the correct card. And I've seen many times where the cards are drawing inaccurately and the well just runs 100% of the day because it's not properly reading the fillage. We want to calibrate those POC cards. Another reason is to optimize the runtime. A lot of wells do not have a pump off controller on them and they're on timer. Do we have the correct runtime? Well, a fluid level shot in connection with a dynamometer test will tell that. Is the fluid level down there at the intake, and how does the fillage look for the complete run cycle that you're watching? Does it maintain 100% fillage, or maybe halfway into that run cycle, it starts to pound fluid? Okay, we need to back off the runtime a little bit. Another thing is to recognize inefficiencies or damage in the system. For example, tagging. You can recognize tagging and then adjust the rods to minimize that damage. You might find there's a lot of paraffin on your rod string and try to do something to minimize that. Here's an example of a well. It shut down due to minimum load. Surface card crossed this dashed line, and this is due to extremely heavy paraffin friction. So in this particular case, the pump is still working. It's still picking up and releasing the fluid load, but we have lots of excess friction that's being recorded in the surface card, and then it's distorting the shape of the downhole card. This would be a well that you'd want to get a hot oiler out there very quick to pump all sorts of hot fluid down the backside to melt that paraffin. So we can recognize tagging paraffin, we can make adjustments, or maybe you might see indications of solids in your dynamometer cards and know the next time we pull the well, we need a desander to try and separate the solids out, or maybe we need a better pump to deal with those solids. Maybe we need to double valve our traveling valve and standing valve. Another reason for a dynamometer test is to measure the diagnostic rod loads. So most of the time when you talk about rod loads, it's based off a simulation, but simulations are not always accurate. And sometimes the mathematic in the simulations is not accurate, or other times the input. Maybe you have a bad deviation survey that's not accurately representing all of the kinks and twists in your wellbore. Well, when you do a diagnostic test, when you're actually on site and you're measuring it, it's going to pick up all the friction that's occurring on that system because it's actually measuring what the load is as the unit is stroking around. So a diagnostic measurement of your rod loading could be quite different in certain circumstances. For example, this one right here, paraffin. When you're doing a simulation on your rod loading, are you plugging in a lot of paraffin friction occurring on the upper end of the rod string? Of course not. So that would be another reason for a dynamometer test. Here's just an example of a rod string. This is with the high strength rods, and this is what the rod loading is. Okay, it's very high right here. You can see it's overloaded on all these. It also has a safety factor on here though that we'll talk about. But anyways, you might want to get a actual measurement on site, weigh the well to see what the actual rod loading is. And then lastly, another reason for a dynamometer test is to identify the cause of a failure. Let's say the well is not pumping, so what is the actual cause of that failure? Or maybe you're trying to diagnose underperformance. So maybe the well is still producing, but it's not performing to expectations. And so what is the cause of that? Well, usually looking at the shape of the cards, and again, if you can get a fluid level shot with it, by looking down both sides, you can really determine what's going on downhole and what is the cause of that underperformance. So these are all the reasons why it's very important to understand dynamometer tests and how to interpret them and how to apply them to your well. Now let's look at two diagnostic tools. Okay, zoom out. We're on a very high level right here. And this is what we're not focused on in this course, but this is the fluid level gun. And it's very important to understand this. So let me give you a slide or two on fluid level gun and how it works. So the fluid level gun, you connect it to the annulus, and that's what I'm hooked up to right here. You can see these wells in the background. I'm just tied onto the outside. It's got a pressure chamber, and you shoot a pressure pulse that travels down hole. It will reflect off the top of the fluid level and come back to the microphone here in the fluid level gun. Now we can see where the top of the fluid level is, and then we can also approximate. We can kind of look down through it and approximate what is the pump intake pressure and producing bottom hole pressure. But the fluid level gun helps us answer how efficiently is the well producing the reservoir. So are we getting all the liquids out that are coming into that particular well? And in reality, are we getting all the liquid out that's above your pump intake? Because your pump can't suck from anything down beneath the intake. All your pumps are going to be positive charge pumps. That means they have to have some sort of fluid head or pressure to push the fluid in. But how efficiently is the well producing all that liquid out that's coming from the reservoir? And another way of saying this is the liquid producing efficiency. So any fluid that's above our intake, are we getting it out of the well? Now, the fluid level gun can't tell you exactly. So this, what I'm saying right here, even if you get a well pumped off, okay, at least for this course, we're going to call that 100% liquid producing efficiency because we're getting all the production that we can. But then you might say, well, that's not necessarily the case. You might have a bunch of scale on your perforations, or maybe you have damage in the near wellbore region that's limiting the amount of fluid coming in. Okay, I'm not going into that in this course. I'm just focused on the existing reservoir, in perforations the way they are, and also where your pump is set. In this example right here, the pump's not exactly on bottom. If we wanted to get the bottom hole pressure lower, we would want to pump the fluid level off to the pump and potentially even drop that seating nipple down to below the bottom perforations. But what we're focused on is, are we getting all the liquid out that is above the pump? And if that's the case, we're going to say our liquid producing efficiency is high, and that's what we want to see with a fluid level shot. Now, sometimes you're not, and then the question is, how much fluid is down there above your pump and your perforations? So the dynamometer is looking at a different type of efficiency, and this is what makes it interesting when you combine these two tools together. So the dynamometer is looking down the rod string, We've got the two different types of temporary installed dynamometers here from eCourse, but the dynamometer looks down the rod string and is looking down to see what's happening at the bottom of that rod string on your pump plunger. And again, how is the fluid load being picked up, carried, and released? And the shape of this card right here would tend to indicate that you likely have fluid pound. But the dynamometer tells us how efficiently is the system operating, or another way of saying that is the mechanical producing efficiency. So let me just kind of give you a scenario to make this more concrete. Let's say you have a well that's pumped off. Okay, and so your liquid producing efficiency, assuming you have low casing pressure, you don't have too high of a pressure, and on a rod pumping well you should, but your liquid producing efficiency is 100%. But let's say it's pumped off, but you're running the well 100% of the day and you're pounding fluid with 50% pump fillage. Well, if that's the case, then your mechanical producing efficiency is very low. Or maybe you have a high fluid level, and so you have a lower liquid producing efficiency, but you also have a worn pump. Your mechanical producing efficiency is also low. So we're looking at two different sides of the well. And what's really amazing with these tools is that you're seeing how much fluid is above the pump. And so you can tell with a fluid level shot, okay, we've got enough liquid for the pump. And what are the pump cards showing us? Sometimes you'll find, and I'll show you examples in this course, where a fluid level shot might show the top of the fluid level right here. And it shows a ton of fluid above the pump intake, but the pump is not feeling it because you have a choked or restricted intake. And so there's something down here. It could be that the TAC is packed off, or it could be that you have solids in your gas separator down on bottom, and that's preventing the fluid that you're seeing on the backside from actually getting up into the pump intake. So usually these two tools are they're complementary in the fact they're usually giving you the same information to some degree, but sometimes the information they're reading is different and both tools are right. There is a lot of fluid in the backside, but then the dynamometer shows it's not coming to the pump, and they're both right. There is a lot of fluid, but it's not getting to the intake. So anyways, that is the beauty of these two tools, because you're looking down different sides of the well. Now with a fluid level shot, you're going to find one of these three scenarios. You'll find the fluid levels at surface with no gas bubbling up through it. So you have pure liquid, not a common scenario unless you have a well that's not currently producing. So you might find a static fluid level like that on a higher bottom hole pressure well, maybe in a water flood. But anyways, that is going to be basically zero liquid producing efficiency, right? There's no fluid coming into the well. Your well is loaded up with liquids. Jumping over to the other side right here, if you have a well that's pumped off with low casing pressure, your liquid producing efficiency, or how well are you drawing down on that reservoir, is going to be essentially 100%. Or you might have something in the middle. The fluid level is not at surface, it's not at the pump intake, and you have some amount of liquid here on the backside that is adding some back pressure to your producing formation. Now, when it comes to your dynamometer test, remember, it's looking at the mechanical producing efficiency. This is your ideal card. Pick up the fluid load, carry it, release it. This is what we want to see. Now, all these other cards right here represent some degree of inefficiency, like you're operating the well with insufficient liquid, or you have sufficient liquid to fill the pump, but there's free gas getting into the intake. Our pump is worn out. We have a hole in the pump barrel on a bottom hole down pump, or the ideal card, except that we're beating our equipment up with a mechanical tag right here. So all these cards here represent some degree of inefficiency in the system. Here's another example of inefficiency in the system, and this is going to be the inefficiency of actually transmitting a sufficiently long downhole stroke length to the movement of the plunger. So this is a unit, a pumping unit with 120-inch stroke length. I took this picture after it shut down due to low pump fillage when it started to pound fluid, and the downhole stroke length was only about 25 inches long, this is terrible. You do not have an efficient means of getting the transmission of the stroke length to the downhole plunger. And that's what matters. When you look at the production rate, it's only based on the relative movement between the plunger and the barrel. And so it doesn't matter what your surface stroke length is for your production. What matters is your downhole stroke length. Now, I showed this card to some people and they said, well, it looks like your plunger might actually be stuck there, like it's stuck in the barrel. That is not the case. The cards look like this. It had a longer downhole stroke length when it had 100% fillage. But even in this condition right here, it was only about 40-inch downhole stroke length. And so this is a bad design to this particular system. Now, why is it so bad? Well, it was a deep well, about 11,000 feet, and it had a relatively short stroke length for 11,000 feet. But really the bad part of the design is that it had about 8,000 feet of fiberglass rods, and they were 1-inch fiberglass rods instead of being 1.25 inches, which you would typically use for that depth. So you have too many fiberglass rods. They're smaller diameter, so we have a really stretchy rod string. We have a short stroke length. We have I think it was 1.5 inch pump, which isn't too big, but essentially this unit was also running slow, so it doesn't have dynamics. All of these factors combined together, we're not effectively getting a long stroke length downhole. So anyways, this represents another type of inefficiency in the system that you can see with a dynamometer test. So lastly, this last slide right here, let me tell you the basics for a fluid level shot. If you're not familiar, I want you to understand it because you're going to hear it referenced regularly through this course as we talk about dynamometer cards. So here is a fluid level gun. Now there is a pressure chamber right here, and you're going to pressure that up with nitrogen. Let's say you pressure it up to 800 psi while your casing pressure is 50 psi. It needs to be something quite a bit higher than what your casing pressure is. But you pressure up the pump chamber, you screw it on to the wellhead, and then you can open up the gun to the well. Now we're in communication with the well. And then you're going to close off the valve to the flow line. So any gas that's coming up the annulus is now trapped. And by closing that off, that's going to minimize the noise of the gas that's flowing up. Also, it's going to concentrate that shot to go directly downhole. And you're going to take the shot, and what's being recorded here on what most people call their fluid level shot, this is actually known as an acoustic trace. This is the recording of the microphone. There's a microphone right in the bottom of the fluid level gun, and as you release that energy, you create a pressure pulse that and that goes down. The microphone is recording all the sound waves that come back to it. And so that's what the acoustic trace is. It's a recording of the sound waves that are coming back. So here is the shot, and this is all of the waves coming back. Most of these are tubing collars right here. You can see the energy starts to die down as it gets deeper, and then you start to get some big reflections back on this acoustic trace. These are due to perforations. As that pressure wave is encountering changes in cross-sectional area, it sends back a reflection that comes up to surface and is recorded by that microphone. And here is the fluid level kick. Now, in order to calculate the depth to the fluid level, first off, you have to identify which is the fluid level kick. So you can see we have all of these kicks going up and down right here. Which one is the fluid level? You have to know how to disentangle it. On this one, it is the bottom kick. But so you have to first identify that. And then secondly, you have to know how fast that pressure wave is traveling. So what is the acoustic velocity? When you take a fluid level shot, you're creating a sound wave in the gas medium. And that shot, boom, that pressure wave travels down through the gas medium. It's basically a compressive wave that's traveling down. And you need to know how fast it travels down and back up. We need to know that speed, known as the acoustic velocity. We need to know that in connection with how long it took for the pressure wave to reflect off the fluid level kick and back to the microphone. And based on that, if we know the velocity and we know the time is recorded up here on this axis. This down here is the depth. But if you know the velocity times time, if I was driving 60 miles an hour for 1 hour, how far did I go? What's the distance? We can calculate the depth to the fluid level. So anyways, that is the acoustic trace. And then, of course, you can see where the fluid level is on different types of wells. You'll find it in different places. This well's pumped off. This one has a higher fluid level. Now, if you look at this acoustic trace right here, or excuse me, if you look at this, this diagram right here, it shows the fluid levels here, and we have liquid, which is going to be oil. If the well's producing in steady state, you will have the oil-water interface at the pump intake. And if it's making gas, that gas is going to bubble up through the liquid because it's lower density. It will flow up the annulus up to surface. Now, this is what we call the gaseous fluid column. Okay, this is called the gaseous fluid column. After the fluid level shot, you do a casing pressure buildup test. So remember, this valve over here is closed. We see how fast the casing pressure increases. So on this particular well, we know where the fluid level is. We took the fluid level shot, we calculated the depth to the fluid level, and then you do a casing pressure buildup test, and you see how fast the casing pressure rises. Well, that represents how much gas is bubbling up into this column of gas right here, and then that goes into a correlation in the eCourse software, which I talk about in the fluid level shot course in quite depth. But the output of that is your model of the well. So your model of the well, if you were to let these gas bubbles rise up to merge with this other gas, and then the liquid were to fall down, this is what the model of the well looks like. So this is our gaseous fluid column, and this right here is what we call the G-flap. This is the gas-free liquid above the pump, and that represents how many vertical height, what's the vertical height of pure liquid residing above our pump. And that's what we want to know, because the pump can only get the liquids that are above it. So how much liquid is still there that we could potentially produce in this particular well. So based on this, though, you can then compute your bottom hole pressures. What is the pressure at the pump intake, the fluid going into the pump intake, and then your producing bottom hole pressure is usually calculated based on the lowermost perforation. So what is the back pressure that is being held here? And that would be contributed by the casing pressure, the pressure due to this gas, which is usually very low, assuming this is a low surface casing pressure. And then you would have the oil column and the water column right here that are all contributing to it. But that is a fluid level shot in a nutshell. I just want you to understand that because you'll hear a lot of references to it in this course. And with that, my friend, this is the last slide. Let me leave you with a little Soviet propaganda, because my wife is Russian. She was born in Soviet Union. She's a tough cookie. Skori vi ponedelnik I snova na robotu, which means I can't wait for Monday to come so that I can go to work. That's how they all felt in the Soviet Union. And I hope that is the way that you're feeling right now as we jump into the course. So remember, as you start that next section, it will have the wrong section numbers.